Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1949 publication in the Physical Review titled Physical Principles Involved in Transistor Action by John Bardeen and Walter Brattain, alongside its theoretical companion piece on the p-n junction by William Shockley, stands as a seminal document in the history of science and technology. It represents far more than the mere announcement of a novel device. It is the codification of the physics that unlocked the solid state, transforming semiconductor materials from objects of laboratory curiosity into the active, controllable heart of the modern world. This text, born from the unique intellectual crucible of Bell Telephone laboratories in the immediate post-war era, laid the theoretical and phenomenological groundwork for the digital revolution. Its importance lies in its elegant synthesis of quantum theory, experimental ingenuity, and predictive modeling, which collectively demystified the behavior of charge carriers in crystalline solids and provided the intellectual toolkit for an entire new field of engineering. To examine this work is to witness the precise moment when a powerful new force in human affairs was given its scientific charter, its principles articulated with a clarity and foresight that continue to resonate through every circuit and processor of our age. The quest for a solid-state amplifier was a long-held ambition, a response to the inherent limitations of the reigning vacuum tube technology. Vacuum tubes were bulky, fragile, power-hungry, and generated considerable heat, posing significant obstacles to the construction of complex electronic systems like the National Telephone Network or emerging digital computers. The dream of a solid-state replacement flickered in the periphery of physics for decades. The conceptual blueprint existed as early as 1926 in a patent by Julius Edgar Lilienfeld, who described a field effect device remarkably similar in principle to the modern MOSFET. Lilienfeld's concept, however, was a theoretical ghost, impossible to realize with the impure materials and incomplete understanding of the era. The true genesis of the transistor required the confluence of two major streams of progress. The first was the development of quantum mechanics in the 1920s and 1930s, particularly Alan Wilson's application of band theory to semiconductors, which provided a coherent model for understanding electrical conductivity in terms of electron and hole energy bands. The second was the intense materials science research conducted during the Second World War to produce ultrapure germanium and silicon for radar detectors. This wartime effort, especially at institutions like Purdue University, yielded crystals of unprecedented purity, making it possible for the first time to observe and control the subtle electronic effects that had previously been swamped by impurities and crystalline defects. It was into this prepared landscape Bell Labs inserted its solid-state physics group in 1945, led by the astute and demanding William Shockley, with the explicit goal of creating a semiconductor amplifier. Their primary intellectual adversary was a phenomenon known as surface states, mysterious electronic traps on the semiconductor surface that seemed to screen electric fields, frustrating all attempts to build a working field effect device. The problem fell to John Bardeen, a brilliant quantum theorist, whose profound insight into the nature of these surface states would inadvertently open a different path to amplification. The 1949 paper is a masterclass in the interplay between experiment and theory. It details the discovery and operation of the point-contact transistor, the device famously brought to life by Bardeen and Walter Brattain in December of 1947. Their breakthrough emerged from a series of experiments designed to probe the very surface states that had thwarted Shockley's field effect approach. In a pivotal experiment, Brattain immersed a piece of N-type germanium in an electrolyte and discovered that he could modulate the surface potential. This led to the creation of the first working device, a slab of germanium with two closely spaced gold foil contacts pressed onto its surface, serving as emitter and collector, with a larger contact on the base. The paper's most profound conceptual leap was the explanation of how this peculiar arrangement achieved power gain. Bardeen and Brattain proposed the theory of minority carrier injection. They argued that when the emitter contact was biased in the forward direction, it injected holes, the positive charge carriers which are a minority in N-type material, into the germanium crystal. These injected holes could then diffuse across the small distance to the nearby collector contact. The collector, biased in the reverse direction, created a strong electric field that swept up these arriving holes, thereby modulating the much larger current flowing through the collector circuit. The gain, or amplification, resulted because a small change in the emitter current produced a large change in the collector current. The paper provides the quantitative physics underpinning this model. It articulates the concept of current gain, designated by the Greek letter alpha, defined as the partial derivative of a collector current with respect to the emitter current, a value of alpha greater than 1 signified power amplification. The authors presented a diffusion-based model to describe the flow of these minority carriers, governed by an equation of the form the second derivative of the whole concentration P with respect to the distance x from the emitter, minus the concentration P divided by the square of the diffusion length L sub P equals 0. This equation demonstrated that for the device to function, the spacing between the emitter and collector points had to be significantly smaller than the average distance a hole could travel before recombining with an electron, a parameter known as the diffusion length. This theoretical framework transformed the point-contact transistor from a black box into a predictable physical system. It was a beautiful piece of physics, born directly from experimental observation and providing a robust explanation for a startling new phenomenon. Yet, even as it was being celebrated, its own theoretical underpinnings pointed toward its obsolescence. The immediate impact of the transistor's invention and the subsequent publication of its principles was immense. The military and telecommunications sectors instantly recognized its strategic importance. For Bell Systems, it promised smaller, more reliable telephone switching equipment. For the military, it opened the door to miniaturized avionics, guidance systems, and portable radios. The initial point-contact transistor, while groundbreaking, was a temperamental device. It was electrically noisy, fragile, and its performance varied wildly from one unit to the next due to the difficulty of precisely controlling the spacing of the contact points. Its limitations were apparent, a fact that deeply troubled the group's leader, William Shockley. Feeling somewhat sidelined by the Bardeen-Brattain discovery, Shockley sequestered himself and, in a remarkable burst of creative insight, conceived of a far more elegant and robust design, the junction transistor. His theory, published alongside the point-contact paper, described a device made of a sandwich of type and n-type semiconductor layers, for example an NP-N structure. This design eliminated the delicate point contacts, replacing them with stable, well-defined boundaries, or p-n junctions, within the crystal itself. Shockley's contribution elevated the 1949 literature from a description of a single invention to a comprehensive theory of semiconductor devices. He formulated the famous Shockley-Diode equation, which describes the current flowing through a p-n junction as a function of the applied voltage V. This equation takes the form I equals I sub s multiplied by the quantity of E raised to the power of the quantity QV divided by KT minus 1, where I sub s is the reverse saturation current, Q is the elementary charge, K is the Boltzmann constant, and T is the absolute temperature. This powerful equation captured the essential rectifying behavior of the junction and became the cornerstone for modeling all subsequent junction-based devices. The junction transistor, based on this theory, was more stable, less noisy, and vastly easier to manufacture with consistent characteristics. It was this version of the transistor, born from Shockley's theoretical vision, that would truly power the electronics revolution. The irony is poignant. The initial point-contact device, the empirical subject of the 1949 paper, was almost immediately superseded by the superior junction transistor, whose possibility was revealed by the deeper physics the paper helped to establish. The long-term evolution of the transistor concept flows directly from the physical principles articulated in 1949. The ability to precisely model and control the behavior of minority and majority carriers within a solid crystal was the fundamental prerequisite for all subsequent developments. Engineers and physicists now had a quantitative language to describe, predict, and optimize device performance. This led to a virtuous cycle of improvement in materials purification, fabrication techniques like photolithography and diffusion, and device design. The ultimate expression of this legacy was the invention of the integrated circuit in 1958 by Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor. The integrated circuit was the logical culmination of the junction transistor's potential. It recognized that if one could create a single transistor within a piece of silicon, one could create many, along with resistors and capacitors, all interconnected on the same monolithic substrate. The principles of p-n junctions, carrier diffusion, and field effects, all detailed or presaged in the 1949 literature, were the essential building blocks for this monumental step. This innovation, in turn, fueled the exponential progress described by Moore's law. The principles also found their ultimate expression in the metal oxide semiconductor field effect transistor, or MOSFET. This device finally realized Lilienfeld's original vision of controlling current with an electric field, but it required the mature understanding of semiconductor surfaces and interfaces that had been painstakingly developed in the decades following Bardeen's initial work on surface states. Today, billions of MOSFET, each an infinitesimal switch governed by the quantum mechanics first harnessed at Bell Labs, form the architecture of our digital civilization. The collective work of Bardeen, Brattain, and Shockley, for which they shared the 1956 Nobel Prize in Physics, serves as a paramount example of how fundamental research, driven by a clear industrial objective, can yield transformative results. The 1949 papers, are the intellectual title deed to the information age. They are documents of immense historical and scientific weight, capturing the moment of transition from the macro world of mechanical relays and glowing vacuum tubes to the quantum-governed micro-world of the solid state. They are a testament to a unique synergy: Brattain's brilliant experimental hands, Bardeen's profound theoretical intuition, and Shockley's ambitious and powerful analytical vision. While their interpersonal dynamics were famously complex, their collective output was a coherent and world-altering body of knowledge. The principles they articulated transformed a simple element, silicon, the primary constituent of sand, into the most powerful tool humanity has ever created. By explaining the physics of charge control within a crystal, they gave us more than an amplifier. They gave us a new medium for logic, for memory, and ultimately, for thought itself. The text of their work, stripped of its historical context, remains a clear and potent primer on the physics of solid-state devices. Read within that context, it becomes the founding narrative of our technological epoch, a story of how the deepest understanding of the material world can give rise to technologies that reshape the very structure of human society.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.